This is lesson 1 in the AS Further Maths Roots of Polynomials pack. This follows on from the Roots of Polynomials stuff that you did in the complex numbers pack earlier on in the year. Just as a quick recap, what you should remember from that pack is about the relationships between the roots of a polynomial and its coefficients. So if you've got a polynomial with coefficients ax squared plus bx plus c, or ax cubed plus bx squared plus c, or blah blah blah. These are the results that you're supposed to know. So the sum of the roots of any polynomial equal to minus b over a. The sum of the product pairs of polynomials is equal to c over a. Sum of the product triples, if you've got them, is equal to minus d over a. And the highest we go up to is the quartic. So the product of the roots of quartic is equal to e over a. You should know these results already, and we're going to use those in these packs. Quite a common exam question, an early exam question on the paper is to ask about finding functions, different roots of an equation, so things like this. These examples here are all very similar. What we're going to do is we're going to combine these together into some standard results that we already know. So currently here, we've been asked for 1 over alpha plus 1 over beta. Now this is not the same as 1 over the sum of the roots. What we're going to do is combine these fractions together. So I'm going to cross multiply by that and multiply the denominators to get a plus b over ab. But alpha plus beta plus alpha divided by alpha beta. Now the top of the root, top of this fraction is the sum of the roots, which we know is equal to minus b over a. The bottom of this fraction is the product pairs, which is equal to c over a. And if you times the top and bottom through by a, you'll get minus b over c. It's not essential that you learn this result, but you need to know how to do it yourself by combining these fractions together. Extend this idea to a cubic, so we're going to multiply the denominators of this together, alpha, beta, gamma. The first term would get multiplied by beta, gamma. The middle term would then get multiplied by alpha, gamma. And the last term would get multiplied by alpha, beta. And what you notice here is on the top, you have the product pairs. Some of the product pairs, which is c over a. On the bottom, you've got the product triples, or products of the roots of the cubic, which is equal to minus d over a. And when we times the top and bottom of this through by a, you get minus c over d. We can finally do the same thing for a quartic, so multiplying all of the denominators together using alpha, beta, gamma, delta. The first term would get multiplied by beta, gamma, delta. Second term, everything except beta. Third term, everything except gamma. And last term, everything except delta. On the top here, you've got the sum of the products triples, which is equal to minus d over a. On the bottom there, you've got the product of the roots of a quartic, which is equal to e over a. And we can cancel the a to give minus d over. Hopefully these next ones are obvious, but using your laws of indices, you can expand powers and factorize and things. So if you've got a to the n, b after the n, b to the n, you can factorize the to the n out, and you know alpha beta then is equal to the product of the roots of a quadratic, which is equal to c over n. Same for cubic and quartics, alpha beta gamma is the product of the roots of a cubic, so minus d over a to the n. And same for the quartic, alpha beta gamma delta is product of the roots, which is e over a. Finally, we have some useful results for sums of squares and sums of cubes. At the very minimum, I need you to be able to derive these results yourself in an exam. You may wish to memorize them to make your life a bit faster, but I need you to at least be able to come up with them. I'll show you where the first results come from. I'm doing all of them. So, for example, looking at the quadratic, if we are asked for alpha squared plus beta squared, it's not just a case of doing alpha plus beta all squared, it's a little bit more than that. But that's our starting point. So, if in the question I was asked for alpha squared plus beta squared, my starting point would be alpha plus beta squared, because I know if I to expand this out, I would get alpha squared plus beta squared. I just get this 2 alpha beta extra. So if I want a result for alpha squared plus beta squared, all I have to do minus that 2 alpha beta across, and this is the result that's given. Now this is useful because you've got alpha plus beta, which is the sum of the roots of a quadratic, which is equal to minus b over a. And you've got the product of the roots of quadratic, which is 2 alpha beta, which is c over a. It turns out if you look at the rest of them, so for a cubic, you're doing alpha plus beta plus gamma squared. For a quartic, you get the same thing. So it turns out, I'm going to write it like, summarize it like this. So it turns out if you're doing the sum of the roots squared of a polynomial, that's equal to the sum of the roots squared. So this one, this one, this one, it's all the sum of the roots squared. Take away 2 times the sum of the product pairs. And again, the pairs there, product pairs there, product pairs there. And this thing that I've written in here, you can memorize this if you like, or at least learn how to derive it. Now, a less common formula to come up is this next one. You could learn these formulas for sums of cubes. I would not recommend it. For the quadratic, you need to come up with it yourself. It's not too bad. So we're alpha plus beta cubed here. So I'm going to do binomial expansion to expand this out. So I'll get alpha cubed plus 3 alpha squared beta 3 alpha beta plus cubed. That gives me the alpha cubed plus beta cubed that I wanted. I've just got these 2 terms here. So if I do alpha cubed plus beta cubed on one side and take that across, minus 3 alpha squared beta plus 3 alpha beta squared. Well, I can factorize out 3, I can factorize out an alpha, and I can factorize out a beta. And it'll leave you behind that alpha plus beta in there. This is useful because what you've got here, so you've got some of the roots cubed, you've got 3 times the product pairs, which is c over a, and you've got some of the roots there as well. So that's useful. This idea doesn't directly extend to higher orders, so for cubic sums of cubes, it's much more complicated, and I would not recommend learning this and trying to derive it yourself is a pain, but I'll show you a way of dealing with this later on in the class. Have a quick look at these and use what we've just done. So this first one, we're going to combine these together to a single fraction. We're told in the question that alpha plus beta equals 5 and alpha beta equals 6, so we get 5 out of 6. For the next one, alpha squared beta squared, well, you can write that as alpha beta all squared. And alpha beta is just 6, so that's 6 squared, which is 36. Now this next one, you can either derive it yourself or memorize the formula. So this is equal to the sum of the roots squared, which in this case is alpha plus beta, minus 2 times the product of the roots alpha beta. So that's 5 squared minus 2 times 6, 25 minus 12 is 13. And then for the last one, again, either you can derive this yourself or you can memorize it. So the result was alpha plus beta cubed minus 3 alpha beta. Alpha plus beta, that's 5 cubed minus 3 minus 6. 125 minus 90 is 35. There are a couple of tricky U tries here, which are much harder than those that we've just done. So I'm going to work through these ones as well. So the first one, we're going to combine this together into a single fraction, but we're not just going to multiply all the denominators together. We're going to be a bit smarter than that. Looking at this, I'm thinking I can make the denominator of this alpha beta gamma. So I just have to times the first term by gamma, I have to times the second term by alpha, and the last one by beta. So what you actually get on here is the sum of the roots on the top. On the bottom, you get the product of the roots of the cubic, so that's my, so you get B over D. In our case, B is 5 and D is 9. Not just multiplying all the bottoms. This one we're going to have to come up with our own formula for this one, and it tells us what to do. So it's going to be a bit of so we're doing the product, sum of the product pairs squared. So alpha beta times all of these is alpha squared. Right as alpha beta squared. Then alpha beta squared gamma, and then alpha squared. Next one times everything by beta gamma. So I get alpha beta squared gamma plus beta gamma squared plus alpha beta gamma squared. So the last one times everything by gamma alpha. So I get alpha squared beta gamma. I'm going to get alpha beta gamma squared. And for the last one, I get gamma alpha beta squared. So notice the way I've done this. These three terms along the diagonal, the ones that we wanted in there. Everything else you should hopefully notice has a factor of alpha beta gamma in common. Some of them are the same as well. So we've got alpha beta squared gamma and alpha beta squared gamma. We've got alpha squared beta gamma, alpha squared beta gamma, and we've got alpha beta gamma squared, alpha beta gamma squared there. So we have two lots of each of those. So I'm going to group these up before I rearrange. Alpha beta. Sorry, like in the bracket. Squared beta squared plus beta squared gamma squared plus gamma squared alpha squared. So that's what's in the question. And then I'm adding on two lots of these because they come in pairs. I'm going to factorize out alpha beta gamma from all of them, and that's leaving behind an alpha plus a beta plus gamma. So factorizing those remaining terms. I can then rearrange this to get what I wanted. So alpha squared plus beta squared gamma squared plus gamma squared alpha squared equals that bracket start off with minus 2 times alpha beta gamma alpha plus beta plus gamma. So this is the sum of the this is equal to the sum of the product pairs squared. So that's c over a squared. 2 times the product of the roots, which is minus d over a, times the sum of the roots, which is. And so here that c over a is minus 11. Minus b over a is minus 9. And minus b over a, that should have been, is minus 11. So working out 1, 2, 1, minus 19. 31. And in this lesson, we're going to look at how you deal with the sum of cubes of a cubic. This was a past exam question that came up, and either you learned the results and regurgitated them, or you didn't have a clue on this one. I'm going to show you another way of dealing with it. These questions are usually multi-part questions. Usually walk you through it a little bit. So first off, we're working out alpha plus beta plus gamma. So we know that that is just equal to minus b over a, which is just equal to minus 5 over 1. It's just alpha squared plus beta squared plus gamma squared. We know a result for this one. So this is equal to the sum of the roots squared minus 2 times sum of the product pairs. So that is equal to sum of the roots is minus b over a, 5 squared minus 2 times the sum of the product pairs, which is c over a, which is 24. And 25 minus 48, so minus 22. Then you could substitute the results that you know into this formula here, which actually is slightly different to the one that's earlier on in the fact. But method 2 is a much better method, which I'm going to work with. Now, in this question, you've already been told alpha plus beta plus gamma and alpha squared plus beta squared plus gamma squared, and now you've been asked for alpha cubed plus gamma, beta cubed plus gamma cubed. Well, in this question here, we have a cubed term. So if our roots are alpha plus beta, alpha, beta, and gamma, if I substitute each of those into here, so just think about alpha for now. If I substitute alpha into here, this will satisfy and it will be equal to 0. So I can get that alpha cubed minus 5 alpha squared plus 24 alpha plus 7 equals 0. And I can rearrange this to make alpha cubed the subject. We can do exactly the same thing for beta and gamma. And then when we are asked for alpha cubed plus beta cubed plus gamma cubed, we can add each of these together and collect up our like terms. So adding each of these together is here. And then collecting up our like terms results in this thing here. This is useful because we already now have the results for alpha squared plus beta squared plus gamma squared earlier in the question. So that was minus 23. We know the sum of the roots earlier in the question is 5 and we're minusing 21. So that gives me minus 1. 5 minus 120 minus 21. 2, 5, 6. Pause the video, have a go at this. You try using this new method, and then I'll reveal the answer to this. I'm just going to look at method 2, I'm not interested in method 1. So I'm going to rearrange to make alpha cubed, beta cubed, gamma cubed the subject. So you get alpha cubed equals minus 4x, minus 4 alpha squared minus 4, 8 alpha plus 5, sorry. So in all of these in and collecting the like terms gives you this expression here. You've had results for this and this, or you can work those out easily enough. And sticking those in, you should get 47. Very well done if you got that.